hello everyone. Basically, yeah, I'll be talking today about PyTorch. As mentioned, I'm one of the original authors, but you know, the author list at this point is very long, and there's a lot of people, both from Facebook and from outside from various academic institutions, who are just random kind of open source contributors who are working on the library right now. So you know, at this point, there's a lot of stuff there. I think there are a few ways we can do this talk, because a lot of it depends on kind of how much do you know about the library. If you don't know very much, I can just do a kind of introductory talk. If you know a bit, I can kind of give you, without like a lot of prerequisites, I can give you an overview of like what are the current directions that we're taking, and what are kind of the future features that we're planning for the library that we're developing right now. So how many of you maybe have used PyTorch, perhaps at least once, who have wrote a script in PyTorch? Okay, so there's quite a bit of you. And how many of you have heard of PyTorch? Like you've probably used TensorFlow or something else, so you generally know what PyTorch is, but okay. Okay, yeah. All right, so probably since like half of the audience perhaps has done something with PyTorch or similar libraries, we'll probably do this slightly more advanced thing, but don't worry, I will also like explain all of the basics so that all the rest of you do not get lost. So basically, if you Google online what PyTorch is, you will probably see that it's a deep learning framework. But and this is kind of where we started from. This is kind of the most important use case we're thinking about, but this isn't really not everything. It turns out that like the needs of deep learning are actually kind of aligned with a lot of needs from scientific computing. So for the sake of kind of introduction, you can really think about PyTorch as if it was Numpy. And really probably all of you, if you've done any kind of data processing in Python, you will know Numpy. So at the lowest level, in case, just to kind of recap, Numpy is pretty much a library that gives you a way to express multidimensional arrays, right? So you have pretty much just those nested lists where kind of the lengths of the lists have to be regular at each nested level. And then you have some kind of type of an object that you're holding. And Numpy lets you hold arbitrary Python objects. Torch is somewhat more restrictive. We only allow you to hold numerical objects, so either integral or floating point values, plus some special cases like complex numbers. And yeah, and basically what you can do is there are a lot of operations on those arrays that you can perform, right? Like you can do, for example, addition of all of the numbers in those arrays is just a single line. And the reason why Numpy is great compared to just iterating over regular Python lists is Python basically uses a highly inefficient representation for data that you would hold like just in a raw list. Numpy and PyTorch, they will use kind of the native data format of your computer to pack the data into memory efficiently, and also kind of utilize pretty much all of the resources you have available to kind of get out the peak performance if you have a lot of data to process. And of course, later you can slice those arrays, like in this line that assigns to D. So this, for example, takes the first and the third column out of the matrix and assigns it to D. You can check the shapes. You can do matrix multiplies with like random matrices just as at the end. And at the lowest level, again, PyTorch is exactly like this. So PyTorch at the lowest level, it's pretty much like Numpy, but it has a lot of nicer features. So the syntax might be slightly different because of legacy reasons. It's kind of a mashup of Numpy and MATLAB at this point for weird reasons. But anyway, I think it shouldn't be too hard to learn. If you just look up functions in the documentation, you should be able to find things easily. But yeah. Of course, there is more. Just redoing Numpy wouldn't be very smart, so there is more. So first and foremost, it's still tightly integrated with Numpy, because this is pretty much the kind of primary language that every single data science package in Python speaks, right? So you have OneLiners that let you convert between PyTorch arrays and Numpy arrays. And the important part about this is that the cost of this is pretty much constant no matter how many elements you have. And this is because the data is entirely shared. Like if you modify the PyTorch array, the Numpy array will be modified as well, and vice versa. So this basically means that like This is nice because if you want to use some of the PyTorch features that are missing in Numpy, or like in another project which kind of can also interface with Numpy, you can just import like torch in a single place. You can kind of, at a single function boundary, you can just kind of convert your inputs, which are NumPy arrays, to PyTorch tensors. You can do some compute on this, and then you can again convert them back to NumPy arrays. And those conversions are pretty much free. So this way you can kind of start progressively porting. If you want to use some of those features, you can start progressively porting existing code bases, which like depend on NumPy or some other packages that use it, to utilize PyTorch at this point. And the primary big point, which is really missing from NumPy, is accelerator support. So we've heard a lot of good things about NVIDIA GPUs, and this is really kind of also the primary accelerator I have in mind when I'm talking about this. There is a bunch of work done on AMD GPUs and also custom accelerators like TPUs and so on. So those things are generally kind of still developing, but they are there, and people are actually using them at this point. And PyTorch makes it really easy to use those things, right? Because this is pretty much a script that just samples like 2 by 2 arrays and then just adds them and prints them, right? If you want to do the same thing, but you want to perform the addition on the GPU, for example, you can do something like this. So if the random constructor, it pretty much will sample an array where like you give it a shape and every element will be like independently sampled from the normal distribution. So you can say that, well, okay, but I want the data to live on a particular device, and this is what you specify with the device argument. And similarly, if you already have an array, which is kind of, the way you allocate y, this is an array, you didn't specify the device, so by default it will be put on the CPU. You can also use the to method to, for example, move it to a different device. And another nice thing is that since, generally for a lot of those use cases, you're dealing with large data, GPUs are kind of perfect for this kind of array processing. GPUs are basically like heavily parallel machines. They have a lot of cores, but they're much simpler than CPU cores. But they're kind of geared towards numerical computation instead of like heavy branching and traversing data structures. So this maps perfectly pretty much to everything that we need to do in libraries like PyTorch. And the line basically at the top of the slide, it will tell you, okay, if I have a CUDA GPU available in my system, let's use this for my compute. Otherwise, let's just fall back to the CPU. And this is nice because this single line pretty much will enable you to like experiment on your laptop, which might not have a CUDA-enabled GPU, and then just send the script to a more powerful server, and then it will just automatically trigger and start using the GPU. So, and the important part is that all of the operations are the same. Like all of the operations are kind of overloaded on the device that the arrays are on. So all of the inputs to a single operation have to be on the single device, but it really doesn't care too much on which device they are. It will kind of automatically adapt. If you give to the plus operator, if you give 2 arrays which are on the GPU, this will run on the GPU as well. So it's really easy to kind of write code which is completely agnostic over basically pretty much any PyTorch code will adapt no matter what kind of device. As long as you kind of set up and put correct arrays on the, like if you have parameters you will have to move them to a correct device. But once you do this, the code is exactly the same, no matter if you execute on the CPU or on the GPU. Alright, and the next feature, which is also kind of missing from NumPy, which is very crucial for machine learning, is really high-performance automatic differentiation. So all of machine learning is pretty much gradient-based optimization, and writing out gradients by hand is not a funny thing really to do, especially if you're dealing with complicated models, right? So there is this technique called automatic differentiation, which basically allows you to only write the function of your model. And since the differentiation is pretty much, there's just a bunch of rules which you have to apply, but it's kind of a mechanical process, this can be entirely automated. And this is something that PyTorch does for you as well. So for example, as an example, in here you have this polynomial function, which is really easy to differentiate in your head if you want to. And basically what PyTorch gives you is you have to kind of tell us which arrays you want to differentiate with respect to, and this requires strata notation. AD, unfortunately, is not free. It especially increases the memory pressure. greatly, so you should not enable this always. But if you do, also do not worry. It's not all that expensive. And basically, what you do is you evaluate your function. So you evaluate, for example, your neural network, or like a polynomial function, or like a simulation, or whatever kind of numerical code you have. And then you take the output. So this is the poly of x in the like grad x line. And you give the output of the function to the torch autograph grad function, and you give the inputs to this function. And what this will do is it will differentiate the output with respect to all the inputs, and it will give you kind of the derivatives as the result. So like if you print x, and if you print whatever you get from the result of this differentiation, you will see that it matches. And the important part about this is that this can differentiate arbitrary Python code. So you can use anything you really want to implement this. You can use coroutines, you can use async await, like no matter what kind of crazy Python features, which like few people use for implementing models really, this system will adapt to it. This is completely agnostic of the source code you use. You can use control flow, anything kind of goes by. So this is like the basic kind of layer of PyTorch, and those are really kind of the crucial features. Yeah, apart from this, like the most heavily used things are a bunch of kind of helpers to structure machine learning models, especially neural networks, which I really don't have slides for in here. I can briefly cover this during our later tutorial. But just for now, we've hit 1.1 release lately, and and I just want to kind of briefly touch the base on what we're kind of working on right now and how we're trying to improve the experience of machine learning research and deployment. So pretty much the problem we've been trying to address with 1.0 is that previously PyTorch is kind of traditionally more used in the research cycles and not so much in the development cycles, and we were kind of unhappy about this, especially that it was used at Facebook AI Research, and they develop a lot of models, and they eventually want to start actually evaluating them on live data on the site, right? And previously, this meant that they pretty much had to take any single model that the researchers wrote, and they had to rewrite this, for example, in Caffe2, which is like an optimized kind of framework for inference, right? And so we wanted to kind of bridge this gap and to make it much easier to like reuse the single code base you used to do research, and to later take this and put this into production. And so also an important kind of mark here, it's also fine to like not use those features if you're kind of running on low traffic. It's completely fine to like just expose a like Flask API, use the regular Python stuff. People are using Python this way, and Python is also used for writing web servers, right? And so this works, and so this is really not strictly necessary unless you're pretty much at Facebook scale, or unless you actually want to bundle this with a mobile app, for example, because you don't really want to bundle the whole Python interpreter. Like in PyTorch, the definition of the model is encoded entirely in the Python code, and so you cannot really separate them very easily. So if you were to deploy this in a mobile app, you would have to kind of bundle the whole Python interpreter with you, and that's expensive, and also like mobile CPUs are very slow. So this would be like, Python is not very fast on the kind of desktop class CPU. It would be terribly slow on a mobile class CPU. So the stuff that I showed you before, the kind of NumPy-like stuff, we're calling this eager mode now, and it has a few benefits. It's really good for research and experimentation because that's just regular Python code, right? You can use any kind of random debugger, you can use print statements, whatever, this just works, right? So it's really simple to write and debug and iterate on this, and it's still pretty fast. The problem is that it's hard to deploy, and also it's kind of hard to optimize because there are some optimizations that can be done automatically, but are still kind of painful if you want to do them manually, right? So basically our answer to this is we've introduced kind of a new programming language, but a programming language, like you don't really need to be afraid of it because it uses exactly the same syntax as Python, and it has exactly the same semantics as Python. The only difference is that it does not support 100% of Python, because Python is extremely complicated, and like a lot of the language features make it pretty much impossible to like reason about what your code actually does before you actually run the code. And this is something which is crucial for the optimizations which we want to perform. So like this is pretty much just a very reasonable subset of Python. So like you cannot monkey patch methods of classes, for example, at runtime, because this would make our life so much harder. But like this is not something that people usually do in their machine learning code, so it actually ends up working out just fine for most of the use cases that our users are interested in. And generally, as I said, the most important features kind of work. You have control flow, you have tensors, you have scalars, you have print statements, strings, function calls, all of the basic collections. You can nest, you can define your own classes, and we're still kind of ever expanding the scope of the language, as long as we cannot make the language kind of inconsistent and impossible to reason about, which is something that I will show you later, and I will be talking about also later. So generally the question is, how do you take your eager program, which you probably use to like implement your machine learning model, and how you change it to a script program, right? And there are two ways to do this, which is tracing and scripting. We like try very hard. It's not like you put those functions in a separate file or anything like that. They live really side by side your regular Python code, and if you just remove those kind of annotations or those tracing lines, you will pretty much just fall back to the Python implementation, and you will be able to again use the regular debugging tools and everything. So tracing is kind of conceptually, in some way conceptually simple, but it also has a lot of pitfalls, which is why I wouldn't recommend this for like a lot of more complex models. I think scripting is like, especially that the subset now is somewhat well defined, scripting is actually pretty pleasant, and we will not cover tracing during the hands-on tutorial. We will only be covering scripting. But tracing, basically what it does is your code actually does not even have to conform to the subset that I've mentioned. The problem is that you will give us a function and an example input, and we will run this function on this example input, and we will kind of see what kind of array operations you did inside the function. But the caveat is that we only see the array operations. So if you have like something like, okay, now read the first element of the array and do this many kind of iterations of the for loop, right? We don't see the for loop. We will only like kind of record how many times the loop executed during this single execution, and we will never like even check if it should execute a different number of times later. So this sounds kind of dangerous, but at the same time it also makes some things convenient. So if you take convolutional neural networks, they're pretty much just a sequence of array operations, right? So it doesn't really matter what kind of Python code you will use to implement this kind of model. What matters is this kind of sequence of different like convolutions and nonlinearities and kind of a data flow pattern. But this is just fine recovered by tracing. So if I were to implement a convolutional neural network, I would probably do something like this. So there is, at the top, it doesn't matter what the NN thing is. You don't need to know the API exactly. The point is, those things at the top, they're kind of the boxes that you saw in this diagram, right? And so, since this is kind of mostly sequential, I'll skip connections for now. If you just have a sequential network, I would probably implement this like that. So I would depending on some command line arguments, I would kind of change the length of the list, add more of those layers, or kind of trim the list somehow, or change the parameters. But then the model is like as simple as just iterate over this list and like just apply every single box that you have, right? So it might seem that you have a loop in here, so tracing is not really the good choice. But this is really not the case, because if you just inline this, like once you fix the list, which is only at the beginning of the program, this builds up your model, and it's completely fine to like rewrite the code as this. You're just kind of too lazy to write it like that. No sane person would do this. You would just do a for loop, right? But if tracing unrolls this to something like that, if you're not going to change the structure of the model, this code will do the same thing every time. So if you just record it once, what it did, this will also be like a valid transformation. So tracing is sometimes useful. If you take any model from, we have a Torch Vision package, which has a lot of kind of pre-packaged data sets, which you can kind of load with a OneLiner. It can even download the data set for you if it's open. And we have a lot of pre-trained models there. So you can pretty much take any of since computer vision models are generally kind of simple data flow graphs with those boxes that I've showed you, they're all generally kind of fine to be traced. So you can take any Torch Vision models, you can trace it on an example input, and this should give you pretty much a good representation of your model, but now running inside TorchScript. And another way is scripting. So again, this time you are confined to the subset of Python, but we do kind of recover control flow and do some, and like we will check that you are actually in the subset. Like it either, you know, you don't get any error and it works, or you get an error and it doesn't work. So, you know, if you're doing a recurrent neural network, for example, this is the case where you want to use script. Like if you're doing machine translation, you will be applying your recurrent neural network over kind of different time steps, right? Because you have a sentence of a certain length, and sentences will have different lengths, right? So you want to have a for loop over the length of the sentence. And so in that case, you really want this for loop to kind of be part of your model, and this is something that is captured by script. But, you know, of course, kind of the standard Python features also work. You can do basic stuff like this. You can, you know, use collections. You have all of the control flow basic stuff. Collections can be arbitrarily nested, and yeah, all of this works. Also, another note is that this actually requires type annotations. TorchScript is like statically typed. You cannot really change the type of a variable, so you have to annotate the types of inputs. Output annotations are actually optional, but then the rest from this kind of annotation, we're able to check if the rest of the program is valid, and we're able to infer all of the types that kind of occur in the program later. And the important part really is that they both mix seamlessly. So like if you put those script decorators and you like call something that has been traced before, this will register as a first class kind of call. And also, if you're tracing something and you have a scripted block inside, this will actually put the control flow from that block into the traced thing. But really, the more important part is that this still allows you to call back to Python. So if you have a function like this, of course you can call that function from Python, and it will behave exactly as a Python function with that code would. But another thing is that from this function you can also call other Python functions. So if for some reason there is something which is not supported, you can kind of momentarily escape to Python, you know, run something like, I don't know, issue HTTP requests, and then kind of come back to TorchScript to like an optimized runtime. Yeah, so you know, you have an example in here. Like if you don't trust your random number generator, you can like get dropout probabilities from a safe random source at every iteration, and that's like a valid TorchScript program. Apart from that, you have classes, apart from that, we have classes. This is kind of taken from, it's a bit small, but this is taken from a real kind of research project from Facebook. And really, the most important goals the most important goals are twofold. So one, you can take, if you add those annotations to your programs, first and foremost, you can take them, you can export them on disk, and later there's like a pure C++ library which you can kind of link to your model apps or something, and using this you can kind of bypass the Python interpreter entirely. You can run those models in those model apps in a resource-constrained environment. And you know, the checkpoints are also very easy to kind of read. They're actually zip files, so you can even edit them. But really, you know, since a lot of people in here will probably be doing research, the more important part, which is also kind of underway, so do not expect, especially the things that I will show you later, do not expect, you know, kind of magic to happen later for every single model that you're implementing, but we're also working on improving performance of the array-based code in Python. So one case is that, well, first, we're kind of bypassing the Python interpreter entirely. So if you script a function and it's kind of slowed down by the Python interpreter, not by the array operations, it might get faster anyway, but this is not always the case for all models, so this is not always a win. I mean, it never makes it worse, but it's not always a win. But the more important part is that we have a lot of built-ins in our operations, and some of them, for example, dispatch to the optimized cuDNN library. So if you have a recurrent neural network, for example, the cuDNN library implements like 6 variants of recurrent neural networks, right? Which is great because those are kind of hand-tuned kernels. There's a lot of man-hours kind of that went into writing optimized pretty much assembly kernels for different GPU architectures and all that. And it's kind of hard to reproduce this on your own, right? But the problem is once you want to implement a slightly custom variation of an RNN, if you want to do research on new kinds of like recurrent cells, the problem is that you're pretty much faced with a 5x performance drop. So I'm actually tracking some benchmark numbers from PyTorch. So you don't have to, the x-axis is time and it's git commits, so even if you could read this wouldn't be very helpful. The important part is that this is time, this is like real time, as in we're developing the projects over this timeline, and this is the time as in how long does it take to execute the given benchmark that we're looking at. And basically the purple line you can see at the top over there, this is like what would happen if you re-implemented the cuDNN implementation using the regular Python code, regular PyTorch code. The blue line here at the bottom, like later it's kind of obscured, but in here you can see that it started as distinctly fast. This is how much time it takes to compute the purple function, but using cuDNN. So you can see that this is kind of heavily optimized compared to that. And all of the middle lines, what they are is that, you can see that we've been kind of developing this project as it went, and what you can see is that if you just add the annotations for scripting, we will be able to rewrite your RNN code to suddenly become pretty much at cuDNN speed. And the important part in here is that, well, okay, this is for an Elastim network, so it's somewhat standard, but even if you change the equation slightly, this will still pretty much run at cuDNN speed, even though cuDNN doesn't really support this network. It does not have handwritten kernels for this. So we're able to kind of generate code dynamically for your network, provided that you will give us this kind of ahead-of-time knowledge. Like we cannot do this if we're just operating as a library, because we never know what kind of Python code you have and what kind of operation will execute next. But if you script your function, we kind of have this insight into the future. We have this insight into what is the exact sequence of the operations that our code will perform, and hence we can actually apply some optimizations which would otherwise be impossible, and this is something you can see on this slide. So in other cases, maybe you came up with something like alpha dropout, and usually, it has a bunch of math inside, and usually this would be like 3 or 4 times slower than the usual optimized dropout that exists today. But if you actually just write out something like this today in PyTorch, if you just script this kind of straightforwardly maps to the script subset, this will generate like a single operation on the GPU that will kind of contain all of the code that you can see in here, instead of executing every single of those operations that you see separately, which saves us a lot of memory writes, and it's generally a lot faster. And all of this is really happening without any user annotations. We do not really want you to kind of tell us too much about your code. A lot of the magic that you're seeing in here is kind of based on runtime profiling. So also another important thing is that your models might not, run at full speed the first time you execute them. If you're benchmarking something, always give it a few warm-up iterations to kind of, because, for example, we're doing this profiling, so we're gathering some information as you run your models, and after a few iterations, when we discover that, well, okay, now we have enough information about your model, we will start aggressively applying optimizations based on what we've seen. It's kind of similar to if you're writing JavaScript. It's also a complicated language that would be otherwise very slow, but a lot of runtimes implement just-in-time compilers, so they will see what your code actually does, and then, for example, emit machine code. And this is somewhat similar to what we're doing in here. All right. Yeah, apart from that, we're also not kind of doing this in the void. There are other projects that are aiming to do something similar. There's XLA from Google. There's TVM that's kind of supported by Amazon, I think, even though it's kind of coming from open source. We're also integrating with those. So yeah, I have a bunch of other stuff which I'm not sure might be interesting for you, since we have quite a few people who are new, so I'll just kind of skip over this. PyTorch also makes it kind of easy to write extensions to it in C++. So if you have some code which is slow in Python, you can just kind of, you have some function that works on tensors in C++, it doesn't matter what's inside. Those 3 lines at the bottom expose it to Python from the C++ side to load it to Python. There is a more structured way if you want to make it into a package, but there is also a kind of hacky way you can use for your research, which is again a one-liner that will compile the C++ code and expose it. And later you can just kind of call it as if you were calling a Python function. Yeah, all right, let's skip this. There's an interface. So you can also, if you really like C++, for some reason, you can also do research in C++ now. This is how you would, for example, do a simple network in Python. This is how it looks in C++. This is how a training loop looks in Python. this is how it looks in C++. So you can see that it's pretty much the same code. You just kind of have to, put up with some annoyances in the syntax of C++. But this works, even though it's kind of in beta right now. Yeah, and also 1.1 came with the TensorBoard release. So if you want to do monitoring of your training, if you want to see like the distribution of your weights or the loss function and plot this, we've been working hard to kind of make this available to you. Finally, I think something that's very helpful for, like, a lot of kind of tensor code is sometimes hard to read because you're saying, okay, well, let's sum all the values along the third dimension. But like, if someone comes across this code, they're like, okay, but what is the third dimension really? So we're working on something called named tensors, which has been proposed somewhere outside the community. Basically, what you can do is now you can have, instead of just saying, well, like having some kind of implicit conventions in your code which say that, oh, well, okay, if I'm representing an image, then the first dimension is how many channels, like how many colors, for example, does the image have, or how many features did my network produce over this image. And then you have some order on height and width, which you generally have to fix in different software packages, which is different orders. Now you will be able to basically give them names. So you will be able to say, okay, give me a sum of this image over all channels. So you'll kind of collapse it to a single or a mean. So you'll kind of collapse it to an image of the same size, but with a single channel, which is like a mean for every pixel with this. And so this is much easier to read. We're also working on that. Yeah, apart from that, there is a bunch of distributed stuff. So it also kind of went under a complete overhaul in the new API. So also check this out but this is like a somewhat more advanced. So again, I will not be getting into this. The important part is that it really kind of gives you very good scaling. So if you're training like vision models, if you have, let's say, 8 computers, it runs pretty much 7 times as fast as if you were running on a single computer. If you're training like, this is, I think, the second language translation. This is like some kind of a language model. It kind of scales worse because those models are more complex, but it still like gives you significant speed ups. Like if you have good connections on 8 machines, it still like executes 6 times faster. So like if you look at some benchmarks published at Facebook, they're pretty much now training models. They cut down the time from 6 hours to half an hour. Using 16 machines, but of course, well, you need a lot of machines to do that with very good connections. And yeah, finally, I've mentioned Cafe2, so a lot of this effort is also coming from the fact that we are merging those 2 libraries. So Cafe2 has been kind of more on the inference side, PyTorch was more on the research side. Now we're kind of bringing them together into a single library. And yeah, and a lot of the stuff that I've been talking about, it's really kind of supported by a lot of institutions, both kind of academic and from the industry. Facebook's kind of the biggest supporter of PyTorch. They're funding a lot of the development. But there is also a lot of other organizations. NVIDIA is kind of contributing some developers who are helping us make it run fast on NVIDIA GPUs, same for AMD. Uber is developing a probabilistic programming language on top of this. If you're interested in doing something like that, like Bayesian models, you can check this out. And there is also a bunch of other people from either universities or from kind of smaller companies or like contractors and consultants who are just kind of helping us out. So if you're also interested in helping us, it's very much an open source project. It's kind of developed entirely in the open. Everything is happening through issues and pull requests on GitHub. So if you're interested in contributing, even simple things like improving documentation, they're like immensely valuable for us because this means that we have more time to develop the core library. So even if you want to do everyone has to start somewhere. So we're very much welcoming all kinds of contributors. So yeah. So that's kind of the core presentation. It might have been a bit dense because, well, we have kind of varying people with varying level of skills in here. So now we'll kind of go into the notebook and session. But yeah, if you have any questions to the presentation, I don't know, maybe we should do them now or should we do? Okay, if you have any questions to the presentation, maybe we can like take 2 or 3 now, and then we'll sit down to the notebook.
Yeah. released TensorFlow TFX, which is like infrastructure for.
Wait, sorry, I couldn't hear you at the beginning.
I said that Google recently introduced TensorFlow TFX, which is infrastructure, right? Is there plans to do something like that around the PyTorch?
I mean, we weren't planning on building any kind of support for building out like, systems that will automatically take your model and scale, because I think it's a really hard problem, and like a lot of models will, take different kinds of inputs and they will be dynamic in various other ways. So we're usually just focused on providing the path that you can, take your Python code, export it, and run it without Python, for example, or just run your Python code. But the way you write your servers, there's 8,000 packages that will let you kind of deploy a server, and maybe you prefer some to the others. So why not integrate this into whatever you're actually using? And it shouldn't be really too hard. Like, it's a one-liner to load this code, it's another line to kind of run this code and get the predictions, right? So in general, it shouldn't be too hard, but the distribution really depends on like your kind of data center architecture and like on your network and how you want to, if you have like load balancers. There is a lot of complexity there. So I honestly don't, like, in PyTorch we really want to kind of build a core set of features, but not in a very opinionated way. It's more of a library than a framework, so you should be the person who's like using those features, and we do not really want to dictate in like what ways you will be using them. So we're kind of depending on the community to build on the opinionated front ends, like VGX would be somewhat opinionated, but otherwise you can really kind of fit it to whatever use case you're doing, and that's kind of the core part of the project.
Yes, it was a very nice presentation, thank you. And regarding the script mode, I'm more like a researcher and I don't do any deployment usually, but people ask me often, and the script mode, based on what I've understood, it's more like for me, for a researcher to just support running my code faster. But I also saw that you recently merged the code base of Caffe2 into the GitHub repository. Is this a parallel effort, or are you planning, for example, so right now, when I understand correctly, you also export to Caffe2 via ONNX, if I pronounce that correctly?
Yeah.
So is this becoming more tightly integrated into PyTorch, or is it still like a separate thing if I want to deploy my model on a mobile device that I would use ONNX and Caffe2?
Yeah, it's becoming more integrated. Basically, we're like integrated how we run kernels. We kind of want to take, Caffe2 has a lot of those like mobile-specific implementations and also some optimized implementations for the operations that we have. So we're kind of merging them together. And TorchScript really is the future interface to whatever Caffe2 does today. So yeah, we're merging them. They're already using like the same kind of tensor data structures in C++, and we're merging kernels and all this. It just takes time because they're two like big and distinct projects. But this is moving along, and this is really kind of the future interface to all of this functionality.
So for me as a researcher, the future would be I just use my Torch script to make my code faster, but then also some industry person could just take my model and deploy it?
Yeah, exactly. There is a one-liner that takes any scripted code and you can dump it on disk and you can load it anywhere you want without Python.
That sounds awesome. Thank you.
One question.
Yeah, I think there was someone at the back.
Yes.
So we have a bias to the front. So.
Hi. So really like what PyTorch does, and I think it's really influential. And I wanted to ask about that influence it has now on TensorFlow 2.0 with their autograph and TF functionality. Do you have an opinion on that? How is it the same? How is it different from what PyTorch does?
I mean, there's a lot of, kind of learning going both ways, right? We kind of started from different, it's like everyone kind of started from different points and now they're converging to something somewhat similar. Like we started more on the eager mode side and then started converging towards the script. TensorFlow started on the let's use Python as a meta programming language to like describe some computational graphs, like data flow graphs symbolically, and then just have a completely kind of different evaluator that you call into from Python, which is opaque. And TorchScript is similar in some ways, but the interface is completely different, right? Because you no longer build up this using Python, we just analyze your Python sources to kind of get this representation that like TensorFlow wanted. And so TensorFlow is now kind of following a similar path. We just kind of started from different points, and now it's kind of converging. As you know, as we're discovering like what are the good usability patterns, what things give us good performance, a lot of those libraries are converging to a very similar interface. But of course, we're doing a lot of like innovations. There's a lot of innovations that are kind of happening in the background that we generally don't talk about so much unless at like specialized venues, because they're kind of implementation details. So like from the front end side, it might seem that they're pretty much the same, but in the background, like a lot of things that are happening are actually somewhat different. But this is kind of technical, so I'll probably, if you're interested, we can chat about this. But I'm not sure if now is the best time to answer, you know, a very specific question.
Maybe last question. There was someone here that was a question before, I think. Yes? Yes.
Hello.
I'm sorry.
You used gradient descent for optimization purpose, right? For optimization of the network.
Yeah,
so,
I mean, as I've said, be careful about this because this is work in progress, so a lot of things might not get very, like, it should never make anything slower for you. If you see something becoming slower, just report a bug report because it should never be the case. But this is very much work in progress. So while certain models like the LSTM will be faster, not every single model will get faster, right, magically. So
actually, I'm trying to apply meta-heuristic algorithm, unsupervised learning method for optimization.
Right.
So, have you tried unsupervised, like genetic algorithm or any other unsupervised algorithm for optimization purpose?
optimization as
optimization of the weights and the inputs and the weights.
Optimization as in, you know, alternatives to SVD?
Yeah,
or?
yeah, SVD.
Well, I mean, it's kind of orthogonal to whatever we're doing, right? It's like, what you're talking about are concrete kind of algorithmic improvements in ML. What we're doing is we're really building systems that let you express the, let's say, alternative optimization algorithms, right? And so, like, you're kind of asking about the research that our users are doing, not about the kind of core library that we're building, which is just a tool to kind of empower people to do the research, like you've mentioned. So me personally, I just spend most of my time kind of thinking about the, you know, engineering side of it, and there's a lot of research in there, but it's like more like systems research and programming language research and stuff like that. So I personally haven't done anything like that. All right. Okay. I mean, we have, I think, like half an hour, 40 minutes, so we should probably move on to the notebooks. All right. So I've put the. Wait, let me pull this up. Yeah, you can see the address in here, I guess. Yeah. Right? But it might be slightly small.
Yes, perfect. Wow.
Yeah, I cannot make the address larger. Anyway, so if you go to, I will just write it. So the address is. So this is the address you have to go to if you want to run this. Basically, something like a lot of the things that I told you, we've been kind of focused on GPU optimizations, and this platform does not have GPUs. So I will actually not be running this on this platform. I will be running this on Google Collaboratory. So you can, if you want to kind of follow me, this script will work, as I've mentioned. I have some conditionals in here that make it kind of device agnostic, so it will work on both platforms. But if you want, you can just go to File, Download as Notebook, and you can, if you have a Google account, you can go to Collaboratory and you can upload it there. And there, if you choose runtime, change runtime type, you can just have like a GPU or a TPU. We'll be using the GPU now. You can just enable this and connect to it, and this will give you pretty much a free instance with a K80 GPU, I think. So this is what I'll be using, but it's completely fine if you just follow in here. It will work exactly the same way, but when we'll be running some kind of benchmarks, you will be getting obviously different numbers because the kind of computation we're dealing with in here will be faster on the GPU than on the CPU. And also our optimizations, since we're kind of more GPU focused, will be more visible on the GPU as well. All right, I'll give you a moment to get started with in any case, this is the address. You can see them. All right, is there anyone who wants more time to start this notebook? Are there people who haven't started it but want to start it? If you raise your hand, I can wait a little more. If not, I'll just go ahead. Okay. Yeah, so I think the stuff that we'll be covering again, it will be mostly focused on TorchScript, but really I will be explaining kind of the bits of the API as we go. You should not worry very much if you do not know the exact interface that we're using in PyTorch. You can read up a lot of it is like easily available online, and you can catch up with this stuff from like other tutorials. But like we have very few like very good TorchScript tutorials, so I think it's better to kind of give you some exposure to this right now. You will kind of catch up on the library if you want to use it later at home, but like you will generally have you will have a general understanding of how can you start using TorchScript as part of your code if you just follow this notebook. So I will be doing everything on screen, so don't worry. You can just try to replicate my steps. At the end, there are some exercises where I'm pretty sure we will not have time to do all of those, or maybe any of those. So you can just try and play around with this. The exercises are mostly just to like, make the exercises are mostly just repeating what we will be doing now together, just so that you can kind of, better remember whatever we did at home. And you can also then do some, offline Googling and find documentation and then anything that you might need. All right, so is everyone done? Did you figure it out? Okay, I guess no one protested, so yeah, let's start. All right, yeah, so we will be mostly, as I've mentioned, we have done some optimizations, not a lot of them, but some of the models that we have looked at are RNNs. And again, we do not promise that this will be fast. We have been mostly focusing on making the user experience somewhat good and the language somewhat expressive. So this is kind of one of the few cases where you will actually see optimization benefits, but there will be more coming, along the way. And another, benefit, as Sebastian mentioned, is that, even if you're a researcher, if you publish your code, people will be, if you use script, people will be able to like use your models kind of in production if they want. All right, so let's get started. So I think both this collab and the environment from the organizers, they have Torch 1.1 installed. You can verify this if you type something like this. So yeah, I have 1.1. You should also see a 1.1 string. So some things have also changed in the latest version, in like the 1.2 release, which will be happening soon. But yeah, for now we're just using this. And now this line you have pretty much seen it in my presentation. So if you run this on the environment of the organizers, you will see that this would probably say device type equals CPU. So this kind of conditionally will select a GPU if there's one available, and otherwise it will just give you the CPU. But this is fine. Don't worry about this. Yeah, so we will be... Okay. I mean, yeah, so if there are people who are not accustomed to notebooks, the way notebooks work are you generally have some cells, you generally execute them in the order in which the notebook tells you, but you can also do this out of order. And so if you like import something in here, this will be like kind of forever visible for all the cells. So if I define fast device in here, if I run this cell, I could, for example, refer to fast device in here. And so if I ran them in order, that would not work. But if I run this cell first and then that cell, this fast device would have already been defined. And to run a cell, to kind of progress to the next one, you just do Shift Enter. And that will execute whatever code you have inside. Yeah, so now we will be again talking about cells, but this time not the notebook cells. We will be talking about a recurrent neural network cells because, so the way, I don't know, how many of you don't know what a recurrent neural network is? If you can raise your hand. Okay, so there is a few people. All right, so generally what you have, if you have a recurrent neural network, I'm not in, I think this is going to erase. I'm not a, very much a machine learning person, so this will be a kind of layman explanation of what's happening in here. But generally what you have is you want to process some kind of sequential data in this case, right? So in general you would have if you have a feed-forward network, you have like a single input, right? And then you just apply like a sequence of operations. It might be somewhat, non-linear, but in general you just have a sequence of operations and you get the output, right? In a recurrent neural network, what happens is that you have a whole sequence of inputs. So you have some input at time 0, you have input at time 1, you have input at time 2, and so on, right? So what you will do is you will want to have some kind of context that will be preserved across those time steps. So this, for example, so generally the way recurrent neural networks are structured is that first you define a cell, and a cell is a function. So I will represent this. I'm not sure if you can see this in the back, but I would represent this with like a big box, which basically has kind of one input from the bottom, and this is the input at the current time step. But to kind of incorporate the historical influence into this, actually maybe I'll just find a picture online that might be simpler. I hope I'll not infringe some copyright. But yeah, generally, well, you have towardsdatascience.com, that's the source in any case. So generally you can think of it this way. What? Okay, thank you. Yeah, so generally you can think of it this way. So to define a recurrent neural network, you first define a cell, and this is the blue block. So orange blocks or yellow blocks or whatever this color is, those are the inputs at every time step. The dark orange or red, whatever, those are the outputs at every time step. But you kind of do not want to do a separate prediction because the past of the sequence might have some influence on how the future predictions should look like, right? So you will also have those kind of intermediate states that are produced by the function in the middle, which will also kind of pass the context between the time steps. So generally this blue function, which is called a cell, it will have two inputs, one for the input and one for the context, and it will produce two outputs. One of the outputs is the output at a given time step, and the other output is the context for the next time step, right? So you kind of have this updating context, which also kind of produces outputs. So you can think of the inputs as like a sequence of words in a sentence in one language, and the outputs will be a sequence of words in another language. But like the predictions for each words are not independent. As you're reading the sentence, you want to include the like knowledge you gained by reading the previous words, which is something that such a model, for example, will let you do. Of course, this is a very simple recurrent neural networks. Generally, you will find more complicated models in the wild, but this is the simplest case, and this is like a building block of many of them. So, for example, we will be looking at something like this. All right. So yeah, so we will now define the blue box, which is a cell. And so we will be using something called an Elastim Cell, which is, again, the standard thing, which is also supported by cuDNN. So you can see that, again, it has some parameters because it's a function that we want to learn. So there will be some parameters. It has the input and it has the hidden. And the hidden state is basically this like kind of context that we're passing between the time steps. And so the context does not have to be a single value, it does not have to be a single array. In case of LSTM, it's actually two arrays. So we will unpack the hidden into two values, and the parameters, we have three parameters in this case. So we take the input, we multiply it with some set of weights, some set of parameters for the input. We add to this some kind of weighted function of the context, and we add some bias just as in the regular kind of linear layer. Then we split this into four parts, we apply some nonlinear functions to this, and then there are just some computations. So, well, okay, we want to mask out, we want to, let's say, forget some information, right? This is some kind of an interpretation, which some people might believe in, some might not. And then you just have some kind of gating mechanism. So I will not be getting into the details of how this works. This is one of the most commonly used cells if you're doing recurrent neural networks. And then what we return, so really, if we want to have, again, a separate kind of output for the output state and for the kind of state tuple, we would have to do something like this. So the output of the cell is hy, and the next state is hycy, because, again, it contains two values. But because we kind of don't want to do this way, we will just return it like this, because hy would be duplicated, right? So yeah. you can just run this, and this will define this function for the next cells. So now the question is, how do we make it recurrent? So there are two helper functions in here that are not very important. So the first one is, how do you define the initial hidden state? Like if you start processing a sequence, you do not really have the context to give to your model, right? So what this code does is it kind of, from the input and from the parameters, it kind of magically somehow figures out the sizes of the context that are appropriate for a function, and then just allocates arrays that are filled with zeros, pretty much. Because we have no useful context, we'll just tell our model that we have all zeros. And you can notice that by using this device, it will put it on the same device as where the input lives. So this is, for example, a code that will adapt automatically to whatever device our computation is running on. And apart from that, again, we have some parameters about the dimensionality for input and the desired dimensionality of the context. And using those parameters, we can allocate pretty much the parameters for our cell. And once we have those helpers, which are just kind of to let us start the process, we implement the actual function, which, we have the cell defined. This was the Elastim cell, and now the Elastim function will do exactly this. So if you give me an input, which is a array with an extra dimension, which is a time dimension, I will just I will iterate. Unbind will kind of give me a list of slices along this dimension. So, well, you can actually do something like this. And so we will kind of slice this array over the time dimension, and at every step we get a step input. We will apply the cell to the step input to the current hidden state, which is the context with the same parameters, and this gives us the new hidden context. And so we will not, unlike this picture, we will not be gathering the inputs at every step. We will only care about the final step, which is kind of, well, what the, how the network can summarize the whole sequence into a single state. One of the exercises is to modify this code to actually start returning the concatenation of those, similarly to how the input was processed. This is an exercise. This is not very complicated. You can try to do this later. So yeah, this pretty much takes it. There is also this part which, if you don't specify the hidden state, because usually the zero thing is kind of natural to do, you might want to make it convenient for your code to not have to care about this too much. This will just allocate it all zero states, unless you provide something in here. All right, so we can run this cell, we can define this, and now we can define, so we will now look at how quickly this runs, for example. So we can take this is a benchmarking function. This line is actually, so there are a few things to cover here, because a lot of people are getting benchmarking their models wrong. If you're trying to make your models fast, there are a few things you have to remember if you want to benchmark them. So first and foremost, if you're running on the CPU, there's nothing you have to do really. But if you're running on the GPU, the operations actually execute independently on the GPU and on the CPU. So CPU is really only when you, for example, add two arrays that are on the GPU, the CPU is only telling the card to add those two arrays, but the operation might not happen, and will then proceed to run the rest of your Python code. While the actual addition on the GPU might execute later, and also there is a whole sequence of those operations that might be kind of the backlog. Usually, when you're running GPU code, you will want the CPU to be ahead of the GPU. So if you want to accurately measure the time your compute actually took on the GPU, you will have to use the synchronize function, which will block the execution on the CPU until all of the work finishes on the GPU. So this synchronization is really crucial if you will be executing on the GPU. You can also read this up in some of our tutorials. Then, again, as I mentioned, it's also important because we're doing a bunch of caching and some kind of benchmarking behind the scenes. It's also important to include some of the warm-up iterations. In this case, by default, we do 5. Just for the sake of initializing those caches, the real training performance will be will get stable after some time, and this is pretty much the, for example, this might be the right time for this model to let it stabilize. So we'll execute it a few times without actually benchmarking anything, then we will synchronize to wait to make sure that the GPU, if we're using the GPU, has finished those warm-up iterations and it's not messing up with our real timing. Then we actually start measuring the time. We run the function a few times, and here 800 times, and we synchronize again because we want to block. And once we know that the whole work has been completed, we measure the end time. So this is kind of a simple way to benchmark this. And then we just subtract, take the difference in the time we measured and divide it by the number of iterations. And that's, yeah, go ahead.
So what is the scope of the synchronize? How much instruction?
Yeah.
Because it's just the following instruction?
I mean, it's like in here, when you execute this function f, which is an argument, it will like add some work on the GPU, for example, right? But so you will add this work 100 times, but since the work takes more time than actually telling the GPU to do the work, this for loop will likely complete before the GPU will be done. So this synchronize call will tell you, okay, I don't want to execute anything that's past that line of code before the GPU actually finishes doing the work. Yeah, go ahead.
Is it possible to synchronize just some words, some jobs that you said? Or there is only this synchronize function?
Yes, it is possible, but you require, in case of CUDA, you have to use streams. We do support that, but it's somewhat a more advanced usage, and we will not be covering this right now.
So, but this would only be for the benchmarking, right? So that otherwise you wouldn't get the CPU.
Yeah. In general, you never put synchronizers in your code unless you're actually trying to benchmark something. Usually there is no reason. Unless you're doing like a complex asynchronous thing with a lot of streams, then you need to kind of make sure that they don't kind of get ahead of each other, and then you need to take care of manual synchronization. You really only need to synchronize. You will never need to synchronize in your training code, which is why a lot of people kind of forget about this when benchmarking, but this is really important if you want to do benchmarking. Yeah.
So if you want to access the output of the network, when you access it, there is an synchronize inside?
Yes, there is an implicit synchronize.
Okay.
Yeah, which is, so generally everything runs asynchronously. If there's some need for the actual, let's say, print to wait on the result, we will synchronize for you. Unless, again, you use complicated streams. Then we assume you're an advanced user and you can take care of yourself. So, but in general, you never need to really care about this, apart from the benchmarks where you just want to accurately measure the time. Yeah, so we do this, and then we can, for example, run so in here we just allocate random input. We don't really want to learn anything right now, we just want to see how fast it runs. There will be other tutorials which will tell you how to run things, how to learn models. This is not the tutorial about this. Then we initialize the parameters. This is one of our helper functions in here. Then we initialize the hidden state because we don't want to benchmark kind of the cost of initializing the hidden state. We just want to benchmark the cost of actual running of our network. And then we say, okay, benchmark the function which just evaluates our model on those initialized parameters, right? And okay, in here we actually say 20 times, maybe let's make it 40 to make it somewhat more stable. Generally, the more times you run this, the more stable this will usually be. So, okay, so we can see, for example, a single with those sizes, if you were to, like your input has 128 features, your context has 256 features, you have a sequence of 164, and you have 32 examples that are processing at the same time, then a single iteration, a single evaluation of something like this will take what, 20 milliseconds, right? All right, so now we can go and actually start annotating this thing with script. So the basic thing is you just add an annotation with torch script. But this really is not sufficient because, as I mentioned, this will tell you that a tensor cannot be used as a tuple. And this is because, as I mentioned, this is a statically typed language, and if you do not provide us with any type annotations, we will assume that all your inputs are assumed to be tensors. So in this case, hidden and params are not tensors, they're tuples, and we want to unpack them here, but this sees a tensor and it says, well, okay, you're trying to unpack a tensor. That doesn't work this way. So if you want to use this, we will be using Python 3 syntax in here for type annotations. It's also generally a good idea to add them to your code. We also need some extra imports which are at the top. So now we will say that, okay, hidden is a tuple that contains 2 tensors, params is a tuple that contains 3 tensors. So this looks something like this. For input, we can say that this is a tensor, and that's probably a good idea, but this is optional since it will be inferred to be a tensor by default. But I'll just put it in just for the sake of having it. And now if you try to evaluate this, you can see that this now compiles fine. And you can see that I didn't put any return type annotations in here. This was just inferred automatically. Now, if you want to do the exercises later, there is an exercise that asks you to implement the MILSTM, which is a variant which is, for example, not supported by cuDNN, and again see how it runs. This actually uses the function phi. This mostly changes how you kind of use those inputs and the context, but the actual transform, which is contained in here, is exactly the same. So now let's just isolate this into a separate function. So we can say something like that. And what do we want to take? We want to do this, and now we say, I think that should be enough. Sorry, can you speak up? Yeah, exactly. So now we can run this, and here you can see that this actually works out fine. But this is a Python function, so it's also a good idea to add type annotations in here. For Python functions, we will not be able to infer the return types. So now you can see that, okay, we have a scripted function which actually calls into a regular Python function, which is something I've mentioned, and this is really important because, for example, now, even if we had a system later where like we have everything scripted, but well, we think we have a bug in this function, we want to debug this, we can actually just kind of comment out this, and this will all kind of keep working, right? So you can revert to Python selectively on some functions and debug them easily. So this works, but if you actually try to investigate what's happening, you can ask for the code that we have produced for this function. You can see that there is this kind of I don't know, dash, and they call to LSTM pointwise, and this dash indicates that it calls outside of the Torch script. This is a simple function, so it actually should just get put into this code. You can see that this is some kind of a representation of your, the code that you wrote in here. If we just enable this script in here and evaluate the, what now? Undefined value cx. Oh yeah, we need to take cx as an argument as well. Yeah, so you can see that in Python, if you don't define something, you would also get an error at runtime. In TorchScript, if this CX was missing and we refer to it now, TorchScript will complain that, well, you have an undefined identifier, we don't know what this is. So this also gives you some kind of ahead of time, guarantees about your code. Yeah, so now if we print this, you can actually see that this call, all of those like sigmoid and tanh and all of those non-linearities, they kind of got inlined into this function, which means that this correctly got recognized as a call to a regular script function. So if something has a .code attribute, it means it has been scripted, and you can investigate like how we see how we represent the function that you scripted internally, right? This is going to be a pretty printed version. There is also graph, which kind of produces a not so nicely looking thing. But if you're like working on compilers, this is interesting. One note is that the code will always show you the unoptimized version. We're doing a lot of optimizations, but there are other ways to actually ask for this. Anyway, yeah, so we have this. Now we will also want to script this because this is also this is also part of our model. Okay, input is just a tensor. Params, again, is a tuple of 3 tensors. And hidden, this syntax is somewhat awkward. Hidden is a tuple of, hidden is a tuple of 2 tensors. Now if you try to run this, it will tell us that it expected a default value and that this value does not really work. And this is because none is not really a tuple, right? So what we have to say is that this is an optional tuple. What now? Expected a value. Oh yeah, and again, if you this is a Python function that is defined in here. If you do not add any annotations, it will again assume that all the parameters are tensors and that the return is a tensor. Again in here, okay, this is a tensor that was kind of unnecessary, but this is a tuple of 3 tensors, and this returns a pair of tensors. So we again need to add annotations even though this is a regular Python function. And now you can see that this compiles just fine without any errors. And again, if we print lstm.code, you can see that, okay, there is this for loop, there is this like call to init lstm hidden, and also since the cell is somewhat simple, it also got inlined into the for loop immediately. So this call kind of got eliminated, so you can also structure your code without kind of worrying about if like the function call overhead will be high or not. Okay, so now we have a scripted model, and the important part is that now with this compiled, this means that this behaves exactly the same as the unscripted model would have. So if you get something to compile, and you only add type annotations, this will guarantee you that it has been changed. So we can just try to re-benchmark this, and yeah, we can see that, okay, we have like a 3x speed up pretty much just by adding this annotation. And so in here you can see the unoptimized code, but if we actually investigate, this is probably not something you want to do. Yeah, so to ask for a specific kind of code that is executed for a given inputs, I will just like allocate those, create those, because we will need to run this. You can ask for a graph bar, and this is like a low-level function. I'm just showing it to you to kind of show that we are doing a lot of processing outside. If we do this, sequence length is not defined. Yeah, so you can see that the actual code that we've run looks very different. If we print this like ugly representation instead of the pretty printed Python code, so this is the graph, this is the same thing that you saw, but in this alternative representation, it's kind of short and it looks somewhat similar. In here, you can see that there have been some crazy things going on. We have a lot of kind of extra functions that have been somewhat lifted. We have some fusion groups, which means that we will generate code for the GPU for this. And so this is how pretty much this code can run faster. But all of this is happening entirely in the background, and like you do not even need to be aware of this. So this is one benefit of scripting. But again, I'm showing this to you because this is kind of a case that we've looked at. This is very much under construction. So you can try to experiment with this on your models, but I do not guarantee that like it will make everything 100 times faster. Generally be kind of, if you see that some other systems make things faster, then we'll probably missed something. You can open a bug request, you can look into this, you can implement this, that would be even better. We can help you do that. But in general, you can also try scripting either because you want to deploy this or because you want your models to be like used in a wider setting. All right, there are some other things in here, but I'm not sure if we have time for that. I'm not sure what time the next talk was supposed to start. 5 minutes ago?
No, yeah,
Ahead, okay. Yeah, all right. So we'll just quickly go into, so another feature in PyTorch, which you will see a lot for those of you who haven't used it, are NM modules. And those are kind of like stateful functions that encapsulate the parameters, right? So generally they will have an initializing method where you will like initialize the parameters. Here we'll just reuse the helper that we've had. And you can also have like a lot of other state. Like you can save those parameters and then investigate them later, unlike with a simple function where you have to pass this around all the time. So generally you will implement init and you will implement forward. And forward is the actual computation that this will do. So in this case, this is a call LSTM module, and we have already a ready implementation given in the LSTM function, which we wrote in here. But generally, I would probably, if I were to do this model, I would just start writing this out as an NM module already. So scripting path is slightly different for NM modules. Generally, I will not be covering a lot of this. We have tutorials for that, so unfortunately it's somewhat awkward. We're kind of trying to make it nicer for modules. But generally, to script this, you need to change the inheritance from an NM module. An NM module is torch NM module. You change it to torch JIT script module. And every single method that you want to get scripted, similarly to function, you say script method instead of script. And yeah, you can try to do this. One caveat in here is that it will actually delay the compilation. So unlike with script where you get an immediate error, if we try to benchmark this now, this will only give us an error now, like a compilation error. And this is because this will first run init and only then try to compile all the methods. So like if you missed some type annotations in here, this will, you know, complain that, oh, well, we have an operator which takes tuples of tensors. We wanted an optional tuple of tensors, but it gave us tensor, right? So you need to add, again, this is like that. And this is like that. And yeah, and here you can see that we can automatically, since we know that those are parameters, we can automatically kind of figure this out. Hopefully that should work. Oh yeah, that's true. Yeah, okay, so this works now, for example. So you can see that the workflow is slightly different, but it is also somewhat similar. So, you know, I haven't explained a lot of, you know, of how the library works. You just got a kind of deep dive. For those of you who haven't used it, you kind of got a deep dive into like what are the latest things. But you know, hopefully, if this kind of got interested to you, if you see some value in the stuff I talked about, you should be able to just, you know, use any kind of regular tutorial. I don't need to come here to kind of give you the regular tutorial. You can read online. Hopefully, this kind of is some kind of an inspiration to actually start learning this. So I think we're running out of time. So if you have any questions, you can either ask them now. If you have questions that you don't want to ask now, you can catch me, you know, either after the talk, during a break, or you can send me an email. You can easily find me on GitHub. Yeah, that's just my handle is first name of my first letter of my name and then my surname. So you can find my email in here. If you want to reach out, I will unfortunately need to leave today, so if you want to catch me at the school, you will have to do this like pretty much at the next break. But yeah, otherwise I'm available at my email. If you have any questions right now, I'm happy to answer that as well. Yeah, go ahead.
Actually, it takes a lot of work to export this for C++, so to be integrated in a...
Yeah, so inside Python, it's just a one line. You can you have torch git save, right? And there's whole documentation about this. You just kind of tell it. You just give it like I can say torch git save, like, you know, LSTM, and say that I want to make it LSTM, but I don't know, some kind of random extension, and this will. All right. Anyway, yeah, that probably works with let's try this. Yeah. In any case, it has some compile time error. But anyway, you can just look up the documentation of this function. This will produce the zip file, and later, you can just do this. Jesus. Yes, you can just do this. So this like torch git load in C++, it's again a one-liner that will load this archive as a JIT model. There's also a whole tutorial, I think, on how to do that. And if there's not, there should be.